Hi everyone, thanks for watching these videos again. I hope you are having a great holiday season so far. So in the previous 4 videos, we talked about classical information in the case of either like a 6-sided die or bit that has either 2 or 6 different states, and those are very distinct states. They can distinctly be in one of those 2 or one of those 6 states. And we also talked about stochastic matrices, which is a way of describing the probability of transforming from a particular state in a particular classical state to another classical state with distinct probabilities. But in today's video, I want to introduce quantum information and the 2 basic ideas of a quantum system and how they are different from a classical system. So in a classical system, we introduced, let's take the case of a bit. A bit can either be in the ket 0 state or the ket 1 state. There's 2 possible states that this can be in. Now, how a qubit or a quantum bit is different is it's not either in this state or this state. A qubit, how it's different is it's represented as, and this is a representation, the symbol psi is a representation of a quantum state, of a superposition of the 0 and the 1 states, where alpha and beta represent quantum states or complex numbers. Well, actually, the combined terms represent the overall quantum states. Now, the idea behind this is kind of confusing, and it's confusing to me, but I encourage you to go and look into this double slit experiment, where basically if you have 2 slits, and there's light coming through the left side of this and projecting onto a screen, and there's these 2 slits right here. The light comes through, and if you have no way of measuring like the individual photons of the light that come through these 2 double slits, then what you see is a interference pattern on here. So basically there's like bright points on here, and there's dark points in between the bright points, and it's very high in the middle, a very high intensity in the middle, and it's very low on the outer portions of the interference pattern. And this result basically shows that the individual photons that come through this screen behave like waves, and they interfere with each other. But if we introduce some sort of measuring device here, then that interference pattern collapses, and we only see individual photons. Now let's return back to the idea of qubits. If you want to learn more about the double slit experiment, I can make another video more comprehensively explaining superposition. But the basic idea of a qubit is it is that superposition or that wave interference of two classical states, the ket 0 and ket 1. Now, the basic idea of a quantum state, or one of the basic ideas, is that these alpha and this beta are always going to be complex numbers. Now, the best way I have to explain this is complex numbers properly explain evolution through time, while real numbers don't do that at all. And I think a good way to explain this is using a matrix. So if we have a matrix 1, 0, 0, -1, which basically takes a plane in the 2-dimensional space and flips it. That transformation applied to a plane flips that plane. Now, if we want to, if we want to say this transformation takes 1 second, right? Then that's okay. We can say this transformation U takes 1 second, and when we apply it to a plane, it takes 1 second. But it's going to be a motion, a continuous time evolution. It doesn't just jump. Like, that's not how the real world works. So if we want to say, oh, can we describe this state at half a second, halfway through its process, then we need to describe some v squared that equals u. And v is that time evolution at half a second. Because we are talking about, oh, let's try to describe this at half a second. But because there's this negative number here in this matrix, there's no way that we can find, sorry, this is v, a matrix V that squares to get u. So the whole idea behind this is by introducing complex numbers, a plus bi, and representing things like -1 equals ei pi instead, or your z equals some re I theta. Now we can properly take v equals square root of u. And the general idea is complex numbers allows the idea of evolution through time, which is how quantum states and how the world works. So that's the first idea of qubits. Now, the second idea of qubits is that these alphas and betas, these operators that operate on the ket 0 and the ket 1, they always form a unit vector, like that. Another way to express this is their sum. Let me get a better way to describe this. If we can explain it like this, the absolute value of this state, or the magnitude of the state vector, is always going to be equal to the absolute value of, let's just say, alpha 1 or alpha 1, alpha 2. Alpha I starts at 1 and goes to 2 of the absolute value squared. And the basic idea of this is that this vector here, alpha 1, alpha 2, is always going to be a unit vector. Because when we square the absolute values of these, we get the probabilities of a state, of a quantum state, either being in ket 0 or ket 1. And when we have complex numbers, we can't accurately describe probabilities. But when we square the absolute values of these what's called probability densities, then we can properly decide what are these probabilities. And these probabilities always sum to 1 when we do this operation. So yeah, those are the two basic ideas of quantum state vectors, or qubits, that these two elements, these two operators on ket 0 and ket 1, are always complex numbers because they properly describe time evolution, and they always form a unit vector because these probabilities always have to sum to 1, because there's 100% probability of a state, of a quantum state, being in one of its possible states. Yeah, because it has to be in a certain state. So yeah, if you have any questions, let me know. Thanks.